In this video, I want to talk about a couple of special cases that you can encounter when using the node voltage method. So before I begin, let's just take a look at this very simple circuit here. So we have an independent voltage source, an independent current source, and then we have three resistors in this circuit. So once again, we find the nodes in the circuit. So here we have this as the node, this one as another node, and finally we have this node too. So we have in total three nodes in this circuit. So out of these three nodes, which ones are essential nodes? As you can see, we don't have any nodes that only are point of contact of two elements, right? So this node has 3.3 elements connected to it, the 100 volt, the 25 ohm, and the 10 ohm. This one also has three elements connected to it, the 10 ohm, the 50 ohm, and the 5 amps. And finally, this one is the point of contact of four components, the 100 volt, the 25 ohm, the 50 ohm, and then the 5 amp. So basically, we have only three essential nodes here. We don't have any regular nodes here. So the next step would be to consider the node with the highest number of branches connected to it as the reference. So that's what we did here. So based on this, now we have two nodes and basically two node voltage variables that we need to find. One is the voltage from node 1 to the reference, and the other one is the voltage from node 2 to the reference. But one thing that you might notice here is that we have this 25 ohm to be in parallel with a 100 volt independent voltage source. So if you remember from before, we said that when we have components in parallel, that means that their voltages are exactly the same. So since this is an independent voltage source with a value 100 volts, that means that the voltage across this 25 ohm is going to be 100 volt. So practically, V1 is 100 volts without us doing any calculations. So when a voltage source is the only element between two essential nodes, so we have this 100 volt voltage source, which is common between these two essential nodes, and then one of those essential nodes is the reference node. The solution can be simpler. So again, here we have three essential nodes, which means that we need to solve two linear equations to find the voltages for the two node voltage variables, but one of them is already determined, right? Because we have this 100 volt independent voltage source connected between node 1 and the reference or the ground. So because of that, we only need to write one linear equation, and that is going to be for node 2. So we have all these currents that we consider to be leaving the node, and then we write the equation for node 2 based on the node voltage variables. So we have V2 minus V1 over 10 plus V2 over 50 plus we have this 5 amp that enters the node, but since we consider it to be leaving, we use it with a negative sign. So negative 5 equals 0. So now let me just quickly rearrange this equation that we have. We have negative V1 over 10 plus 1 over 10 plus 1 over 50 V2 equals 5. And also we know that V1 equals 100. So based on this, we can find the value for V2. So doing this, we get to this result. The value for V2 is going to be 125 volts. So that is something that you should always keep in mind, that if you are working with a circuit in which you have a voltage source that is connected between two essential nodes, and one of those essential nodes is actually the reference node, that means that the voltage at the other node is already known. You can think of it the other way too. So if you have, let's say, an independent voltage source somewhere in your circuit connected between two essential nodes, and still you haven't decided which node that you can consider to be the reference node. So why not choose one of those nodes that is connected to this independent voltage source as the reference node? So that way, one of your linear equations is completely eliminated. So think of it both ways. So that was the first case that I wanted to talk about. Now let us take a look at the other case. The other case is that we have a voltage source that is common between two non-reference essential nodes. So that is the minor difference between this case and the previous one. For the previous case, the voltage source was between the reference and another essential node. But here we have a voltage source that is between two non-reference essential nodes. So how can we solve this special case? So let's just take a look at this circuit first. Let's just go through their steps one by one. Let's just find out what are the nodes again. So we have this node, this node, this node, and finally we have this node, or like any of the points on this line, right? They are all the same because they are all connected and there is no component in between them. So overall we have 4 nodes here. How many regular nodes do we have? Regular node was a node that was a point of contact of only 2 elements, right? So we don't have any of those. So all of these 4 nodes that we have are essential nodes. So let's just consider this to be the reference or the ground because it has more elements connected to it. And then let's just number the rest of them. We have 2, we have 3. One thing that we soon notice is that node 1, the voltage at node 1 is already known. Why? Because we have this voltage source that is connected between node 1 and the reference. So V1 is already known to be 50 volts. So that means that one less equation that we need to solve. But for node 2 and 3, we don't have this condition. So let's just write down the KCL for each one of these nodes. I write it in terms of the currents that are leaving node 2. So for this, for KCL for node 2, we have V2 minus V1 over 5 plus V2 over 50 plus, what is the current that goes through this current controlled voltage source? What is the current here? Do we have any equations that gives us the current for this voltage source? So to answer this question, you have to remember what we discussed about voltage sources and current sources at the earlier lectures of the course. We said that for voltage sources, we cannot know the current that goes through them unless we have solved everything in our circuit. For the current sources, we don't know the voltage across them until we solve everything in our circuit. So the answer to this question is there is no equation that shows the relationship for the voltage of this voltage source and its current. So because of that, I just simply write it as I. I just consider the current that goes through this voltage source is I. So I just, for now, write it like this. Let's just do the same for the KCL of node 3. Let's see what we have. So we have 3 over 100, V3 over 100 plus this current, which is going to be -4. So what about this current? What is this current again? Again, we have the same issue as the previous equation. We don't know that current. But since I already called it I, let's just go with I. So since I is going from node 2 to node 3, if I want to write it here, I need to write it with a negative sign here. So we came up with two equations here. So we were looking for two equations only. Why? Because V1 was already known. So, but does these two equations provide enough information for us to be able to solve this circuit? No, because we have V2 and V3 as unknown. We also have this additional I that we basically don't know what to do with, because we don't have any equation that shows the relationship between the voltage of this voltage source and the current that goes through it. So what happens if I add these two equations together? Let's just see what happens. We have, let's say I call this equation 1, I call this equation 2. Let's just add equation 1 and equation 2 together. Let's just see what we get. We have V2 minus V1 over 5 plus V2 over 50 plus I plus V3 over 100 minus 4 and then minus I equals 0. So we basically summed up the two sides of these equations. So what happens here? We have I here with a positive sign, and also we have I here with a negative sign. So what happens is that because we summed these two equations together, we made this I variable to disappear. So if I rewrite this, now we have V2 minus V1 over 5 plus V2 over 50 plus V3 over 100 minus 4 equals 0. So as you can see in this equation, we don't have I anymore. So this way we were able to eliminate the variable I, that we didn't know what was its value and we didn't have any way to know its value either. So I call this equation 3 now. So we wanted to find values for V2 and V3, but now we only have one equation. We still need another equation to be able to solve this. So one thing we know is the relationship between the voltage at node 3 and the voltage at node 2, because we have a voltage source in between them. So what is that relationship? So considering that the positive side of this voltage source is connected to node 3 and the negative side connected to node 2, we know that V3 minus V2 equals 10 I phi, right? So that is the equation that we can get because we have this voltage source connected between these two non-reference essential nodes. Another thing that we know is that we know how to calculate I phi. So I phi is basically V2 minus V1 over 5. So the conclusion based on these two equations is that V3 minus V2 equals 10 multiplied by V2 minus V1 over 5. So this will be our fourth equation that we have. So using equation 3 and equation 4, we can find the values for V2 and V3. Remember, we already knew the value for V1. So that is the way that we can solve this circuit. So these are all the steps that we had to go through the calculations. But based on these equations, an interesting concept appears, which is the concept of a supernode. Basically, a node that consists both node 2 and node 3 here. So the nodes that are connected by a voltage source. So this is what we call as the supernode. So keep this equation in mind. So this equation, keep this equation in mind. So the KCL holds for regular nodes, for essential nodes. We saw that already. But KCL also holds for supernode. Basically, we consider the combination of node 2 and node 3 as a supernode, and we write the KCL based on that supernode. So let me just go to the next slide where I write the equation for the KCL using this supernode. So how do we do that? Practically the same as before. The only thing that is not there is that we don't even consider this voltage source that is in between. We just write the current that leaves node 2 goes through 5 ohm as before. So it is V2 minus V1 over 5. The current that leaves node 2 and goes through this 50 ohm, which is V2 over 50. The current that leaves node 3 goes through this 100 ohm. It is V3 over 100. And the current that leaves node 3 and goes through this independent 4 amp current source, which is negative 4. And we equal that to 0. So as you can see, understanding how a supernode works can help us reduce the number of algebraic equations that we need to write. Even if you don't know that, following the procedure from the previous slide, you should get to the same conclusion, because if you look closely, this equation is the same equation that I wanted you to keep in mind. So equation 3, right? But here what I did was that I went through all the individual steps to get to this. But now that we know how the supernodes work, we can directly write this equation. And then we do the same. We do the rest too. We consider V1 to be 50 volt. We consider V3 to be V2 plus 10 I phi. That is equivalent to having V3 minus V2 to be 10 I phi. And for the I phi, we know that I phi equals V2 minus V1 over 5 volts. And based on those, we can calculate the value for V2 to be 60 volts. What is the value for V3? If V2 is 60 volt, so this is 2 positive negative 60 volts. That makes I phi to be 60 minus 50 over 5, which is 2 amps. That makes V3 to be V2 plus 10 I phi to be 60 plus 20 equals 80 volts. So this is how we can use supernodes to simplify our circuit too. But again, keep in mind that to be able to use supernode, you should have a voltage source connected between two non-reference essential nodes, right? So in this video, we went over a couple of special cases when we are using the node voltage method. The first case was when we have a voltage source that is connected between two essential nodes. One of them is the essential node, the reference node, and then we saw the case for which we have a voltage source that is connected between two non-reference nodes, and we use the concept from supernode to write the equations and solve the circuit.